Hey everyone. My name is Alex Turner. I am the program manager for the VB and C# compilers at Microsoft. And I'm here today to talk about Project Roslyn. This is the effort that we have to rewrite the compilers in managed code, and more specifically to expose their internals, to expose the code analysis engine, and expose this out so that you guys can target the compiler and write great services against that. By the time the end of this talk comes around, I'm hoping all of you guys can do these three things to some degree. Really, the core is to be able to articulate the purpose, scope, and goals of Project Roslyn. We're going to go over that pretty soon. And ultimately, you're going to be able to build these kind of rich, code-aware tools. The idea is that we're going to expose these APIs out and let you target Visual Studio extensions that really dig deeply into the IDE experience a lot more easily than you have before. And you're going to be doing this by using certain APIs. And we're going to look at a small set now, but hopefully you'll start to feel comfortable going out and exploring, looking on your own. So if you've been to these kind of languages, futures talks before, we've talked about compiler as a service. You may have heard Anders Heilsberg talk about this before. We kind of introduced this whole idea at PDC 08. And, at the time, seemed like a good name. We've realized since then, sometimes there's confusion when we call it compiler as a service. People are thinking we're talking about a compiler in the cloud, something related to Azure. Certainly uses you could imagine for this, but that's not really what we're going after with that name. We're really just talking about exposing the compiler internals as an API that you can target. You think of the compiler today, it's really more of a black box, right? You have source code that comes in one end, right, and out the other end pops a binary. And there's a lot of rich data that's built up along the way. The compiler has to figure out exactly what types you're referencing, what types you're defining, what everything binds to, and it builds up this huge amount of data and then just throws it away once it spits the binary out. And so we want to give you access to that. And so the way we're doing this is we're doing a full rewrite. It's been about 10 years since we first had the C# and the first VB.NET compilers. We're rewriting these in managed code. So we're rewriting the C# compiler in C# and the VB compiler in VB. And we're not just rewriting the compilers, we're also rewriting the language services. This is the bit inside the IDE that provides all the rich code analysis. You think of IntelliSense. You have to know a lot about the code that's been written, the code in this method, the rest of the file, other projects, in order to know what to show when you type dot anywhere and you want to show a completion list. And so the same analysis APIs that enable us to build IntelliSense, to build go to definition, find all references, things like that, that's what's being rewritten. Roslyn's also about scripting APIs. And so we have this idea of taking in a string, right, and being able to parse that code and bind it and execute it, and do so in the context of some sort of host. And similar to the kind of stuff you see today with the DLR, but we want to bring that to C# and Visual Basic. And the other kind of environment where you do that kind of really live editing of code, the other kind of workspace is read-eval print loop. If you guys have played with F# at all, you've seen the F# interactive window. And really, we're trying to get to a world where we have that same thing for C# and for Visual Basic, that rich kind of exploratory environment where you can pull classes in, define methods, sort of the immediate window on steroids. And there's the thing I hinted at before, this idea of language service extensibility. Today, there's plenty of tools. You have tools like Refactor, tools like ReSharper, you have CodeRush, these kind of things where people are going ahead, they're building entire language models themselves, right? Just so they can dig into source code. And there's a huge amount of work you have to do just to get started so you can write your first little bit of IDE work. And even once you're doing that, you almost have to make your own UI for everything. We don't make IntelliSense easy to dig into. You can add your own items. It's not something that's easy to do now. So we want to be able to provide all the right hooks so that you're really just implementing the core logic that you want to provide. And so we've talked about this kind of stuff before. We're digging into a lot of detail today. We're really starting to get more broad. And one thing people ask, we have a CTP out there playing with it, is when they can get a hold of it. So I just wanted to address that early. We like to say the ship date is vnext plus n, where n is greater than 0. So vNext in this case is Visual Studio 11, the release that's going to come out, target Windows 8. So all this Roslyn stuff is not going to be part of that release, but it's going to be part, hopefully, of some future release, a release after that. And so just to get a taste of the kind of stuff I'm talking about, let's just drop into Visual Studio quickly. So what you see here, I have a console app, and it looks just sort of like Visual Studio 2010. I've removed some of the toolbars to make room. But you notice one different thing here. Up in the tab, it says Roslyn. And that just indicates that the Roslyn language service is loaded. You might notice a few other things like the Visual Basic style procedure separators that we have. We're exploring different things we can do there. But if I just take a look here, I can do various things. I can select this double literal. And you see I'm getting a smart tag. If I pull this up, I'm able to have these kind of rich actions, these code actions that are being surfaced here inside the IDE. And for example, I might say, oh, well, what if I want to introduce a local for 4.0? And it's showing me a preview of what that looked like. And so I say I want to do it for all instances, and it's telling me now I can rename. And so I'm going to kind of do this live rename right here in the file. And I commit that. And now I want to go pull out this expression here. Let's say I want to pull it into its own method. So, OK, I selected this, bring it down again. I do this kind of extract method thing. And again, it's showing me that preview. And not only that, it's picking an intelligent name. It's saying, hey, you probably want to call it get circle area because we see you assigning it to a variable named circle area. And so just this whole kind of idea that people can plug in, that you could easily write these kind of things and provide this functionality into the IDE, we think is really exciting. So let's go back and take a look at what actually is involved here. So at its core, again, Roslyn is really about rewriting the compiler and offering these compiler services out. And compilers at its core are going to be made up of a certain basic parts, the parts you expect from a compiler. The obvious parts, so like the parser. The compiler itself, it's going to take in C#, it's going to take in Visual Basic code, and it's going to parse that, turn that into a syntax tree. And so this is where you're going to get sort of the pure syntactic representation of all the tokens and all of the structure within your code. The compiler is also composed of a symbol table. This is going to keep track of all the names of things that are encountered. So if you have a class C, if that class has a method M, those symbols are going to be gathered in the symbol table. And the symbols are more than just the code that you wrote. It's also the metadata that you reference. If your project is referencing MS Corelib and other BCL types or third-party types or your own assemblies that you produce, you're going to pull those in as metadata. And so the symbol tables track that too. Now, sort of the biggest box is this binder box. We like to think of the binder as really the heart of the compiler. It's certainly the heart of the language semantics. If you think of a lot of the differences between C# and Visual Basic, it really gets down to the stuff that goes on in the binder, stuff related to overload resolution. For example, the parser might parse a tree that says, oh, we're calling method foo. But the binder's job is to look at the types of the parameters coming in, first to even determine what those types are, and then use those types to determine which overload we're actually going to produce, we're actually going to emit IL for. And that's that last stage. Once we figured out and we've bound everything in the parse tree and we know what it means, we can then decide to spit out IL. Right? And if you sort of look at this from left to right, you can squint and see what the compiler does today when you call into CSC or VBC. And you're producing a binary. Some text to parse comes in, and out the other end, you get a binary. So what we're really trying to do with Roslyn here is provide an API over each one of these components, providing a syntax tree API that lets you get rich access to this syntax tree. You don't have to just wait for the IL on the other side. Rich access to go directly access the symbol table and see what symbols the compiler's tracking and be able to ask intelligent, awesome questions from that. Doing binding and flow analysis. So speculative binding. Hey, if I was to bind some token here, what would it bind to? That's important to know if you want to make a refactoring safe and avoid collisions. And also flow analysis, figuring out where variables are used and not used. You'll see that later. And also this emit API. And once you have all this data and you actually want to manipulate it, now you want to spit out a binary, you can go ahead and do that. And so once you have these various APIs, you can start to build all the core language services, the things you have in VS today, you can start to re-implement those atop this public API. And these just become then the sort of default set of things that are in there. And they're no easier or harder to write than something you'd provide, something that you might choose to write. And look at the syntax tree API, you have formatting, you have colorizing. That's something you can do just purely looking at syntax. Looking at the symbol tree, remember where things are defined, you can do navigate to. You can hit F12 once you've bound, you figure out, hey, I know what this token means. I bind to it, I hit F12, I can go to definition, and I can navigate through and figure out where that is. And then for the emit API, you have edit and continue, obviously. Once we are running our program, you want to be able to modify that at runtime and spit out a modified binary. So that's a slide we've kind of shown before, but now that we're really fleshing out the API, we want to think of this in a different way. You can sort of picture that whole previous slide condensed into this row. And so these are the 4 core APIs we were just discussing. And so at this sort of compiler tier of APIs, you have those core sort of low-level compiler APIs, and you also have the scripting API that we talked about for having this direct access, providing little snippets of code, having host access, maybe setting some globals that the script should have access to. But really, at this layer above, we want to start abstracting over this kind of stuff, right? I mean, you look at the syntax tree API. We actually have a C# API and a separate VB API for that. And this was an explicit design decision. We explored potentially having some sort of common syntax tree nodes, but you quickly realize if you want real full fidelity, if you want to figure out to the low levels exactly what's going on in the code, you need something specific to each language. There's been projects to try to unify that stuff before, and you end up losing a lot of detail. So these languages in the bottom are all language specific. And where they start to get unified, you come up and have this workspace API. The workspace API, you can sort of loosely think of it as representing your sort of universe of code, your projects and solutions that are aggregating code together. And you can have some of these projects refer to other projects. This is really where you start to get that kind of language-neutral representation of the world. And at this layer, once you have that, you can start building services there. You can build a code formatting service that's going to go in, and sure, it'll have some language-specific formatting logic, but you can ask it to format a document, and it'll figure out the right thing to do. You can also have find all references. If I want to find references to token foo, they might be defined in some VB project here and a C# project there, and I want to find all of them. And so we think of these language-neutral services and the service layer that's above there. And then there's sort of this third tier. We're calling this editor services. Again, these names are temporary for now. If you guys have better names to help distinguish this, please let us know. We're still early on in this process. But for editor services, you think of this as the stuff that's closer to the IDE. These are things like code actions, things like classification, so you know what to colorize, things like completion, filling out IntelliSense lists and being able to richly interact with that, and also outlining. I'm going and deciding what regions I'm going to expand and what I'm going to let you dig into. And these are things that you can provide at the IDE level, and they really care about the specifics of VS. And so we have these 3 different places that Roslyn can add value. And so if we sort of dig into the details of these, really at that bottom layer, the core API is going to be this syntax tree API. And really, you think about syntax trees, this is going to be something that really matters throughout the Roslyn API. We need some way to communicate the shape of the program around. The syntax trees turn out to be that currency, that common language that all the API surface area speaks. And because it's so important, we had to do a lot of thinking to figure out how we make the right kind of trees that work both for the core compilation scenario and also for the IDE exploration. And so some of the core design principles are up here. One of the key ones is that this really represents a set of immutable types. Once you create your syntax tree nodes, you can't modify them. Think of it similar to the string type. Once you make a string, you're not actually mutating the string. When you concatenate strings together, you're actually just producing a new string. And it's a similar idea. Once you produce a tree, you're never actually destroying that tree or changing it. You're always just producing new trees. And we'll see how that works. The other aspect here is that the trees are complete. A lot of other syntax trees you might encounter in different environments, they'll only represent the sort of core stuff you need to compile, and they'll toss overboard things like white space, they'll toss comments, and end of lines, things like that. And that's fine if you're just trying to do an end-to-end compile, spit out a binary. If you actually want to have this interactive language model, you really can't get rid of any of that. Imagine a refactoring that, after it's done, has maybe deleted a comment that it thought wasn't important enough to track. So if you want full fidelity, you have to track everything in the code. We also think of these syntax trees as being resilient. And what we mean by that is resilient to error code that wouldn't compile if you built it. And this is critical for a tree that is also going to serve as this IDE representation. If you think while you're typing your code, you go to a new line, you start typing, and you type foo dot. And once you hit dot, sort of by definition, you're in the middle of the line. So your code is not going to compile at that point. But that's exactly when you need to see a completion list. So in these error cases, we need to have the tree fully fleshed out, even if some of the nodes are going to be these kind of error nodes that just represent things that are unknown at the moment. And we have to have good error recovery, so for future lines, we don't invalidate everything else in the file, because the thing you're saying dot on might be some class defined after the class you're modifying. And the last thing is all of the stuff we talked about really has to be efficient enough to operate at the speed you're typing in the IDE. And it doesn't mean that everything has to complete within a tenth of a second as you're typing, but it means you have to be able to run efficiently in the background. And that's really the core reason that we're using these immutable types. Now, you might think this kind of immutable tree transform, wait, I'm copying all the nodes, how could that be efficient? But we'll see very shortly exactly how we pull that off. So let's take a look at an example, get a feel for the syntax tree API. What we have here is a simple class, class C. The code's there. We have one method m defined. And there's a little comment at the end after the class. And so if you think of this in terms of the sort of core spine, the core structure of the syntax tree, you have one compilation unit at the top. This is just what we call sort of one base file document kind of thing that we're operating on. It's really each unit of compilation that you provide. It's a C# spec term. But just think of it as a file for now. And inside that file, you have one type declaration. And so that's class C. Inside there, you have one method declaration, void m. And that method declaration is composed further of parameter list in a block. Now, this is just the core structure. The pink nodes you could think of as non-terminals if you've seen compiler internals before. But the other nodes, the blue nodes here, are the tokens. This is actually what was encountered in your file. And these nodes represent the actual meat, the actual stuff that you wrote. And you see here, this is what tells us that the type declaration is a class. It's what tells us that it's named C, what tells us that the method declaration has type void. And you see we also have the braces represented in your code. Now, again, I said these trees were complete, so those were the tokens. What we actually have attached to the tokens is this thing we call trivia. And the trivia represents sort of the rest of the file. These are things that don't impact compilation, but they do impact this idea of round tripping, right? And so you imagine here, like after the closing brace, you see on the third line, the one after type declaration, the compiler is remembering that after that token, we have a comment, and then after that comment, we have an end of line. And so it's keeping track of all the spaces, all of the other stuff you have in your file, like comments that doesn't matter for compilation, but does matter when you want to manipulate code, because you don't want to stomp on any of this. So just remember that this kind of trivia is here, but we're going to kind of ignore it for now. So let's assume we want to do some simple transform here. We have void m. We want to introduce some new parameter of type integer here. And it's going to have name x. This is what we want to do, just a simple tree transform. So one way to write that is what you see here. So you could assume we have some variable that's pointing to a method declaration called method, and then we're able to go through and get the old and the new lists. So you see we're starting off method.parameter list. We're digging down to get the parameter list, and we're going to call that old list. This is the list that we're starting with. And this is what we're going to find in the tree and replace. And then there's something called new list. That's what we're defining. And we're going to define that by saying, hey, let's update the old list. And we're calling it update method, but remember, it's immutable. So we're not actually changing it. This is just going to produce us a new list that we can work with. And we're saying, all right, take this new list and have it, for the open paren token, just use the one from the old list. And you see below, for the closed paren token, we're just using that one from the old list too. And this means that we're going to easily pull along any trivia, any comments that are attached to those tokens. So that's goodness for us. Then for the parameters, you see that, well, I'm actually tossing the old parameters list. I'm not referring to it. And I'm simply saying, all right, make a new separated list, make me a new parameter that I can put in that. And you see I'm specifying that the type is int and the name is x. OK, so I've given myself this list of 1 parameters, putting that in, and otherwise I've created this new list. And then after I've done that, I go basically back to the root of the tree, and I say, all right, take the root of the tree, replace that node that was the old list, replace that with the new list, and return me a tree that has that one node switched out for the new node. And so this is how you can imagine you make these kind of changes in this immutable world. So this is one way I could write this. There's actually an even simpler way I could write it, where for the parameter list, I just go ahead and leverage the parser. I say, all right, just parse int x as a parameter list, as one string. And I just produce that and stick that in. And so if you take a look at what that looks like afterwards, you see this here. So I'll go to the before. You see the parameter list just has empty parens. And now we have a parameter in there. And so this is now the transform that we did. But how is this efficient? Like, remember, efficiency is important in this immutable world, and we really care about that. So if you think about what actually has to change to do this kind of replacement, even if we can't modify the nodes or modify their list of children, we still don't have to touch every node here. The core thing we're changing is that parameter list, right? We're swapping it out. We're making a new one. But you notice we already reused the open and closed paren. So those tokens actually are the same objects we had before. So I'm changing out the parameter list. That means that the method declaration that its parent is, that one's going to have to change because its child list is changing. But all of the other children nodes don't have to change. I'm just changing the method declaration. And when I change that, I have to change its parent, the type declaration. I change its parent, the compilation unit. But that's it. So if you see the list of nodes I'm changing here, it's really just the stuff that I decided to explicitly change, plus the parents all the way up to the root. And all the other nodes are reused. And so when I call replace node, that's what's actually going on here. It's replacing the one node I told it to, and then stitching up all the parents. And so you see here we touched about half the nodes. But you imagine some giant tree that we have, maybe 10,000, 100,000 nodes in it that represents a really big source file. If I'm making a change, I might be modifying 5 nodes over here, and all I have to replace are its 5 ancestor nodes up to the root, maybe 10 nodes out of 100,000, so a fraction of a percent. And this kind of trick, this kind of functional data structure, this immutable structure, is how we get away with having immutability, but also have the performance we need to enable rapid edits. And the benefit this gives us, this immutability, is that we then have snapshots. So you could imagine that somebody is doing this background processing. Maybe it'll take 10 seconds to figure something out about the code that the user asked about. As that's happening, the user might go on and start editing the code. We don't want to prevent them from doing that, but we also don't want any logic that's thinking about the code to have to deal with random edits that occur to half the code while they're looking at it. Maybe they already made some evaluation about the first part. So this kind of immutable structure lets you keep that snapshot. And as long as you're looking at it, it's never going to change. And only later, if you choose to, you could go back and get some sort of updated snapshot. So then this idea of compiling, right? What is compiling? Well, it's taking these syntax trees that we've got, that we parsed, taking the set of references that you provided, and putting them together. And that is a compilation. And it's really as simple as that. You take these components, and what do you get? You get the symbol table, the stuff that we've evaluated and found that you've talked about and bound from other assemblies in your own source code. We get a rich semantic model. We can go and bind this stuff, answer a lot of interesting questions about your source code. We can also do flow analysis, go dig through and figure out when variables are used. And also, finally, we can go ahead and omit that. something our compiler is reasonably good at today. So let's actually go poke in. It's enough slides. Let's see what it's like to actually use this API. So I'm going to go back here, and I have a simple Roslyn demo project. You see that I've got inside references here, I have references to both the compiler's layer, this is that low layer, and also the services layer, but we're not going to use the services layer right away. So here in the compiler layer, you see I have the same kind of usings that are pulling both of these in. They're in the Roslyn namespace. So I'm going to use the toolbox to pull code in during the demo, so you don't have to watch me type a whole lot of stuff. So what I'm pulling in first is use of this syntax tree API. So I'm saying parse compilation unit. And I'm providing here a string, right? In this case, it's a string literal. You imagine maybe it came from a file, maybe it came from a network stream, some sort of scripting environment. It could be anything, but here it's a string literal. And it's a pretty simple type. It's class C. Inside there, you have one field, long X, and we're setting it to 0. That's all it does. All right, and so I've pulled this string in, and I've actually parsed it. I'm parsing it as a full compilation unit, so you'd imagine that in its own little file. And I'm going to get back the syntax tree. And so once I have the syntax tree, I can start to answer interesting questions. So I can start to say, all right, well, dig down into the syntax tree, start from the root. This is, if you've used Xlink, kind of link to XML APIs, this kind of thing looks familiar. Go to the descendant nodes, dig through, and then start to use link and say, all right, find me, of all the descendant nodes, find me ones that are field declarations. And take the first one. We happen to know there's only one, so that's fine. All right, so we get the field declaration. Now, once we have the field declaration, now we can go and get that field declaration's initializer. So go to the field, go to its declaration. A declaration can have multiple variables. You imagine like long X, comma Y, comma Z. So take the first of those variables. We know that that first variable has an initializer. We're going to call through that. We're going to get the value. So this whole expression is digging all the way through the program to go through and get that 0 value out. And we're going to start exploring that. All right, so now we have our source code. We've dug through it. We've done about as much as we can do syntactically without actually binding this against real types. So now I'm going to do the other half. And you see, this is these two halves of compilation that we talked about. I'm creating a new compilation, giving it the syntax tree. So I'm giving it the tree that we pulled in, that we parsed. But I'm also giving it a reference. And you see the reference I'm giving here. I'm using a little trick to find type of int and get its assembly location. I'm passing that in. That's going to just be the a location of MS core lib. And I'm going to pull that in. That's the only reference I need. And so I pull in the syntax tree I've got that I parsed. I pull in the reference. I put them together, and I have a compilation. And now I can answer questions from that big binding box. I can answer the next level of semantic questions. And so the semantic question I want to answer here is about conversions that apply to that particular 0 that we found. And so you see, what I'm doing here, once I have the compilation, I'm saying, all right, take this compilation, and among the things you can do here, there's all sorts of stuff. I can add more references, get all sorts of interesting info, but the one thing I want is the semantic model. And the semantic model represents all that binding info I can figure out. And once I get that model, that represents the whole tree, I can get info for some particular node, right? So in this case, I care about the expression node, that's 0 that I was looking at. Okay, so I pulled the 0 in, and I want to start poking at it and looking at it. So once I have info here, you see there's all sorts of data that I can get. So now I can say, all right, what's the type of that 0? That's something you can't tell just from parsing, but you have to figure out what context is it in. It probably has a certain type. It has like integer. That's the raw type that you see. But then it also has a converted type. And so that's based on the context. I happen to be using this int 0 in a context where the initializer expects a long, because that's the type of X. And so this is going to be converted over to long. And so we'll see. I'm going to print out these 3 things. We'll run the app. And we see that's what we get. We're getting spit out here. The first thing is the type of the conversion, the implicit conversion. It's an implicit numeric conversion. The type of 0 is int, as we'd expect. All literals, unless otherwise specified, or all integer literals, show up as int. And it's only implicitly that they get converted to long if you're assigning it to a long. And so we see that's the converted type. That's the actual type that would be applied. So, this is something we can now dig into. And you imagine you're writing some refactoring or some interesting code that's going to try to manipulate this. You might care very much what the actual effective type of that is, right? I mean, here you didn't need to specify a conversion. It was implicit. But maybe if you're extracting this code out and you're going to return it from another method, maybe it's no longer a literal and the conversions don't apply. You need to know what the compiler is thinking here so you can write these kind of rich operations that are going to operate against your code. And so this kind of data and having it really there at the surface is sort of the foundation of being able to build really cool IDE features like that. So this is the sort of the compiler layer. Let's take a look back here. And so remember, we saw that compiler layer. That was really that bottom tier. That was the language-specific stuff that's going on that we want to then start to build higher level services on top of. And so if we think of that first tier, what we build above it is really things that are going to start abstracting over multiple of these compilation units. And so that's this workspace API. So the workspace API, you think of as that next tier. Instead of sort of raw compilation units that I'm pulling apart and dealing with manually, I deal with documents. You think of a document as being closer to a file, right? Something that is part of a project, and that project could be part of a solution. But this is not necessarily a physical file on your hard drive, right? Remember that kind of interactive Windows scenario? Well, take a look at that. There you have sort of a virtual project. It's not necessarily on disk. It's just logically a project, and you want to be able to operate with it that way. And so we have all of this up here, and that immutability guarantee is still working, right? So all of these nodes all the way up are still immutable. If you modify them, anything in the file is going to sort of dig upwards and modify these nodes to, not modify them, but replace them and produce a new tree next to it. And so one core benefit, and one of these ways we get efficiency is, so not only is it immutable, it's also sort of lazily initialized. So you'd imagine you have a solution today, it might have like 1,000 projects in it. You don't want to have to load data for all of those projects if you're just going to work on one. Maybe that one project refers to two others, but it's often its own little island. You shouldn't need metadata for the whole universe unless you actually need it. And so you'll see here, when I'm in a document and I want to dig to its syntax tree, I only actually will parse the syntax tree when I first ask for it. Before then, it won't. And you think of the project in the same way. It represents the compilation, right? Because it has the syntax trees from the documents. It also has the references that are specified for that project. But until we need the compilation for some purpose, we're not going to generate it. We're not going to dig down to that layer. And so we've talked about all these sort of pink nodes all the way down, these as being the immutable nodes, right? But when you're working in an IDE, there is this idea of mutable state, right? You're working on documents. Documents have a very specific current state. However many snapshots you took, the user sees one view of their document that they consider canonical. And that's really what the actual workspace type is for. This sort of, you could think of as the mutable analog to the solution type. This represents the active state of a project or a solution that's being worked on by a user at a given time. And this really makes sense when you start to think of how you modify solutions in this kind of environment. And so it's something here where, okay, well, we want to make an edit, just like before where you saw us replacing things. We're going to make some sort of edit. It's going to bubble all the way up, and we're going to end up with this modified solution. We have sort of the before and after solution. It could be a code edit in one little file, or it could have been us adding 10 new files or new projects or so on. And so we have these kind of edits, and you could think of them as these different snapshots in time. And ultimately, maybe this was a refactoring, the user's deciding if they want to do something. When they actually say, yes, let's commit it, you then apply that final solution back to the workspace, and that becomes the new canonical view of the world. This would then be the file you'd save out to disk if you were working in an IDE. And so we have this workspace, and the way it knows what to do and what edits to make is it has some sort of host environment that's sitting on top of it. And so the host environment could be Visual Studio, it could be a read-eval print loop, it could be some sort of automation layer or a command line tool or something, but something that's manipulating that workspace. And so in the case of VS, you get key presses telling you to modify certain files that'll be changing the workspace. And the workspace will be sending those changes to the solution and keeping track of what the latest correct version of that solution is. So let's take a look at what we could do with this workspace API to start to manipulate these projects in an easier way. So we're going to go back to the demo and clear out all this stuff. And at this point, we're going to be loading a different solution. So you see that what we're going to start from here is something where we say var workspace, and we're going to load a solution from disk. We're loading this MS Build solution, or a solution composed of MS Build projects. And if we just want to take a quick look, I can show you what this looks like. Really, we just have this solution. It's got 3 projects in it. Not very complicated. Class library 1 has just a single class A that's got a protected int field here. Class C has a public const int. Sorry, it's not a field, it's a constant for A and for C. And then, class B here is defining a long field in this case, and it happens to be initialized by talking to both of those constants. And that's possible because the references for class library 2 are talking to number 1 and number 3 like that. Not too complicated when you look at it in VS, but think of a lot of the interconnections that are going on here. You really can't parse and understand what this means until you know about the tokens that are in the other 2 files. So you really do need this strong connection in order to get going here. And so if we go back to our demo here, so all right, so I'm loading this in. I'm going to have my workspace. Now I want to do the same kind of analysis I did before. I want to figure out what's going on with that particular initializer. So I'm going to, or before we do this, actually just even make sure this is working. You can see the kind of stuff that I can do with a solution. I can loop through the projects that are in it. Again, a workspace has one particular solution snapshot that's considered current. And then that snapshot's going to have projects. I loop through, display the name, and then display all the documents in that project. And if I do that, you see we've got this here. We're loading A.cs, B.cs, C.cs. These are in all these different class libraries. So that's good. So, okay, we have this here. I can now delete this. And so let's actually go ahead and find the document that we care about. In this case, the document we care about is B.cs. This is within class library 2. So this is just a sort of a simple, This is sort of a simple link query here. We're going through, we're saying for the workspace, dig into the projects, find the one whose display name is class library 2. And then for the project, find the one where the display name is B.cs. And so we're going to dig in, and we're going to load that one file. So now that we've loaded the file, we have the document here. We can then go ahead and get the syntax tree. And you remember before we had that string and we specifically asked to parse the string. We don't have to do that here because the document represents that string. It represents the state of a given virtual file here. And I'm able to just ask for the syntax tree. If that requires parsing the tree, it'll go ahead and do that. It'll take care of caching that tree for me so I don't have to manage it. I can just think about the document. And so I go and I get the syntax tree. And then in the tree, I'm doing basically the same code you saw before. And so I'm going tree.root, getting the descendant nodes, getting the field, getting that field's initializer, and getting the value. So the same stuff I was able to do before, but I got the syntax tree in a different way. And so one thing here, let's actually just take a look at the expression just to get a sense of what's going on. If I go here, I can look here at the expression, and I see that remember, in file B, that initializer expression I had was c.x plus a.z. And so we can see it's showing us a preview of just the code for that. But if we want to see it in context, there's more we can do here. And so you see there's a visualizer that's registered here, the Roslyn syntax visualizer. And if you get the Roslyn CTP and you're poking around with this, one of the samples that's in the CTP is this visualizer. You can install it, set it up, and you'll be able to go explore inside the trees. And so if I actually go explore here, I can see, yes, this is where I was in the file, right? So my code found class library 2. It found class B. Inside class B, it looked for the first field declaration, found its initializer, right? And you can see how it went from field declaration to the initializer, which happened to be this add expression. right? And so if I was exploring this programmatically, I could dig down to the left-hand side, and I could dig down to the right-hand side, and I could explore that further and figure out whatever I wanted to know. But in our case, we happen to want to know just the same stuff we wanted to know before. We want to know what's the effective type of this expression and what kind of conversions are going on. So I'll pull this in. This code, again, basically looks like the code we saw before. The one difference is when I'm on the document here and I'm getting the semantic model, I'm no longer getting a C# specific semantic model as the return type. I'm getting this generic I semantic model, this one that's common across both Visual Basic and C#. And so I happen to know in this case that I'm dealing with a C# file, and so I'm going to cast that down, or actually, rather, I'm going to get the semantic info, which is also general, and I'm going to cast that to the C#.semantic info, so I can do C# specific things. Again, we really care a lot about having this rich, full language fidelity. There's certain things we can do with this common layer. For example, I can say info.type. I can talk about converted type. Those are things that are concepts in basically all languages that are statically typed, but the idea of implicit conversions, that's sort of a core C# concept, and VB has narrowing conversions, and it's a different widening conversions. That's a different kind of thing, and we didn't really want to have to squish them together. That's the way to sort of lose that fidelity. So if you want C# specific information like implicit conversion, then you go and you get that specific type. So we now have the C# type. I'm saying here, info.implicit conversion. I'm able to do the same checks I did before, and when I run this, you see I'm able to get the same data. But even though we're outputting the same thing here, you can think about a lot more that we're actually doing, and a lot that Roslyn was able to do for us that we didn't have to write ourselves. We're able to figure out that this expression had type int. Like if we go back here, basically that this expression happens to be c.x, which we bound, right? To bind that, we need to know that C is actually type C from this other project, and we need to know that its x value is going to be some constant, right, of type int, and the same for a.z, and that when you plus two of those constant integers together, you get another integer that's still constant, right? And if you're just parsing arbitrary code files, that's a lot of stuff for you to think about, and whoever's writing this code could have done something slightly differently. So having all that built-in language understanding that you can leverage and just do the core language exploration you want is really what provides that foundation, what lets you go build really interesting IDE stuff. And we're going to see one of those next. So that was the Workspace API, right? So that's that kind of language neutral layer. You start to deal at the project level. You're able to navigate back and forth between projects. In this case, all those projects were C#. You could imagine some of them were VB, but as long as they were all in scope and we could figure out what their metadata was looking like, that would be fine. So now you think of that third level, the sort of real core value that you want to add. And this is the level where we really see you guys plugging in there, either as extension authors to help the community, or writing add-ins for your own company to do code check invalidation, or your own style rules, your own kind of business rules that you want to enforce on your source code. And so we can take a look at some of the ways that stuff works. Really, one of the coolest parts is this idea of code actions. You saw sort of a preview of that at the very beginning. And a code action really is nothing more than a transform of our tree, potentially all the way up to the solution. It's an edit, so it's sort of a before and after state for the trees. And it provides all the data necessary for an IDE to both commit that edit and also even to show a preview of the edit, because we have those two snapshots and we can take the difference between them or alternately show them. So an action is that kind of before and after, represents something that the user could do. And you get an action in one of two ways. So there's sort of the issue flavored actions and refactoring flavored actions. So if you look at code issues, a code issue, you could sort of generally think of it as like a squiggle in your code, some sort of issue, either a warning or an error, or something you want to surface to a developer. So if you have your own rules about naming, maybe you want to make your own code issue that deals with naming and helps you enforce those kind of rules. And so this is called for every applicable node. When you make one of these issues, you specify what the scope for it is. And the IDE service takes care of figuring out when to actually invoke your issue to figure out whether a given node actually matches. And if it does, you can choose what to do about that. You can choose to insert a squiggle into the editor. You can have that squiggle show up in the error list alongside real compiler errors that the compiler itself is surfacing. You can provide, additionally, one or more code actions. And so those code actions can say, well, here's an issue, but I'm not just going to tell you about it. I'm also going to provide you a thing you can click on to fix it, if it's something that the compiler can figure out how to fix for you. And so, beyond that, so then you can imagine that's when something is explicitly wrong, but there's also more opportunistic things you could choose to do. And we call those code refactorings. And so these are just contextually available code actions. Right? And the idea is that, and you saw this earlier, you select some bit of code, and this is some part of the code you want to do something to, maybe that 4.0, the double literal. And you have a set of code refactorings that are loaded, and each one of them gets to say whether it applies to that particular selection you have. And if it does, that refactoring then goes ahead and provides code actions. And those are the ones you saw in that list. When I was digging in, I selected 4.0, I pulled down, and there was the extract method one that we had. There was the one about extracting out a local, so that 4.0 became its own local, its radius local. So these are the two different ways that we end up getting an action. So let's actually dig in, and let's see how we can put all of this together to make a quick fix that solves some need we find that we have. So I'm going to go back here, and I'm actually going to just make a new project. Say here, file, new project. And we look at the new project node here, and we see there's a Roslyn node. This Roslyn node, when you install the Roslyn CTP, it puts in a bunch of project templates, things to help you get started, either as a blank console app or starter kits for various things. We want to make a code issue to start off, and I'm going to call this my first quick fix. So I'm going to create this. It goes about creating it. You see that we have here the Roslyn compilers and services layers that are pulled in again. And we have very similar references to last time, but we're also starting to pull in these kind of VS references. This is because we're operating now at this third tier where we're not just talking about Roslyn compilers and Roslyn services, but also directly interacting with VS. And so we see here, all right, well, I have my code issue provider. It derives from or implements iCode issue provider. This is that Roslyn type. And it's decorated with a meth attribute here. So if you've seen any of the extensibility kind of stuff in VS lately, the new way that we do extensibility, we do it through the Microsoft extensibility framework, the Magic Extensibility Framework. That framework is what actually lets you go and just decorate stuff with export attributes and discover those at runtime. So these extensions are going to be sitting in some folder, and we're going to be able to discover those, just like we discover the Roslyn language service. We pull those in and load them into the VS process. So I'm defining this code issue provider. We're saying that it applies to C#. If I actually go down and look, so there's not too much to this code issue provider. Really, the core of it is this get issues method. This is where you're going to define the actual logic that says whether a given node has an issue that you want to surface. And so the way you do it, really the stuff that comes in makes sense. You're getting in a document. And the other core thing you're getting in is a common syntax node. Right? And this is something that could be any kind of node. It might be VB or C#. We happen to be doing C# here. But then this is that kind of node. And I would be able to explore this and figure out what I want to know. And so in this case, if you look at the default code issue that you get here in the template, this is doing something kind of silly. Basically, it's looping through all of the nodes, but when it gets a node in, it's going to look at that node's children and say, all right, well, so for all the child nodes and tokens within this node, let's take the ones that are tokens and convert them to tokens. So now we're going to have this IEnumerable of common syntax tokens. And then for each of these tokens, just do something pretty blunt, get the actual just text that is represented in the editor, and then see if it contains A. And if it contains A, we give this very useful warning that says that your token contains the letter A. And then we go here and we actually produce a code issue that's a warning. So I'm going to run this now. And if you think about what I'm looking at now, this is VS. It's plain vanilla VS. I happen to be referencing some Roslyn APIs, but I'm referencing just like I'd reference any other APIs. I'm using normal Visual Studio 2010. However, when I run my project, I'm now loading another instance of VS 2010. And this one has, if we go and look here to the extension manager, this one has the Roslyn language services. So this is part of the Roslyn CTP that it puts in replacement language services that enable all this functionality. And you see the other thing it has is my first quick fix. So when I've run this, it deployed my quick fix into this separate instance of VS that has its own separate registry hive and is kept isolated. So we're not dog fooding this yet. There's a lot of limitations in Roslyn in the first CTP, but you get a hold of it when you're in this running instance of VS, the one that you're targeting. So I'm now here, and I can go and load up this quick fix demo code I've got. And it's just pretty simple code here. It has some int declarations inside a main method. But you see we have some interesting squiggles here, and it's telling us, all right, static has the letter A, main has the letter A, program has the letter A, right? So we've gone through and we've looked at all these nodes. We didn't filter. We just kind of looked at everything, figured out what had an A, and surfaced this warning. I could even go here and look at the error list, and I could see I now have 6 warnings in the error list, right? So this is surfaced as you'd expect inside Visual Studio, and all I had to do was just specify that simple filter on a node, and VS does the rest to make it behave properly, not block the UI thread. It takes care of all that complicated muck. I just think about the logic that I want. So I'm going to close this now. All right, this is kind of silly, so we're just going to get rid of this. Let's do something more useful. So we think of what kind of code issues we could want to highlight. How about something where we identify locals that you have inside your method and figure out which of these locals could actually be a const local? Which one of these do you compose from other constant things like literals or previous constants and that you never modify later in the method? Those are things that are good candidates to be constant. So, all right, let's think about how we'd actually write this. So we'll go to demo 3 here. The one thing I want to do first, though, is the thing we're going to be surfacing an issue on here are local declarations. That's the only thing that could be made constant in this way. So we don't need to be called. No, we don't want them to call get issues on every single random thing that's in the syntax tree. So we're actually going to specify one more parameter on this mef attribute and say up here type of. And then I'm going to say type of local declaration statement syntax. And so that basically, I only want to be called when there's a given local declaration that I could analyze. And so, all right, now that I have that, I can go here, cast a node. And I know that I'm only getting local declaration nodes. So I'm just going to cast it directly to that type and move on. All right, so now I can start to party, right? What do I have? I have this syntax node, so I can do this first level of testing, the sort of base level on tier 1, which are these syntactic tests. What are things I can know just from looking at the syntax tree? I haven't bound, I haven't thought about references or anything yet. And so, I start to do some pretty simple tests. Well, the most obvious test is let's take a look at the local declaration and see if it's already const. If it's already const, we don't want to be telling people they could make a const. So we're checking if the modifiers have the const keyword within them. If they don't, or if they do, we bow out. The second thing is we're going to need this containing block, right? So we care about local declarations. They're in either a method that has a block or they're in some sort of sub-block. That's the scope for the local declaration. And so when we're looking to see, is this local declaration modified, or is this local modified later on, that would disqualify it from being const, I care about the scope of it. So I'm going to look for this containing block. If for some reason this is some sort of error code, then maybe there is none. If I can't find one, I bail out. And the other thing I do is I need to make sure that all of the declarations that are involved here have an initializer. So you saw we have something like long x equals 0 or int y equals 2. If I have that, we're good. If I just say int y, I can't make that const because I didn't give it a value. So I have to make sure that for all of the variables that could be in this declaration, do each of them have an initializer? If any of them don't, we bow out. All right, so these are the syntactic tests. We've passed these tests. You have to think through what you're writing, but these are all things that are at the level that I want to think about. What does my const test actually mean? And so I'm writing this kind of stuff. All right, so I've tested the semantic or the syntactic stuff. So now I want to think about things that involve binding. So I go and I have my document. I get the syntactic model like I did before. And now I can start to do the more interesting tests. So I can say, all right, well, we know that all these variable declarations have initializers, because we parsed it, there was an initializer there. But the initializer could be calling a method, or it could be dealing with reference objects, things that I can't treat as being constant. And so I want to make sure that each of these clauses, each of these initializer clauses is actually const itself. So I'm going to go through and say, all right, well, for all the variables that are declared in this statement, dig through and get that variable's initializer value, that expression. For that expression, go ahead and say, for the initializer, I want to get semantic info for that initializer. And then once I have the semantic info, test, see, hey, are any of these that I've selected out, are any of them not themselves constant expressions? Are they not things that the compiler could treat as constant? And so we have this nice thing on iSemanticInfo which says, is this a compile time constant? Because that's a concept that's shared enough across the languages for us to provide this. And so we say, all right, if any of them don't say that they have a constant expression as their initializer, well, that's another reason to bail out, because it can't be const if you're calling a method or something like that. Cool. So now we've done sort of one half of our meaty test. We've figured out if the initializer expressions themselves are const. So now we need to do the other half. We need to take a look at the rest of the method and say, did we modify this later? It's all well and good for us to say int x equals 3, but if later on I say x equals 5, that's another reason I can't make it const. So now what I want to do is something even more advanced. I want to do this kind of flow analysis. So this kind of looks like a lot of code, but if you look through it, each part of this makes sense. Remember I got that containing block up top. That was sort of the scope within which somebody might be modifying it, the scope that I have to go check to validate that. And so I want to be analyzing data flow within that bounds, right? And so the bounds I'm talking about is going to be from the end of the declaration. So I declare x, there's some sort of semicolon, everything after that is what I care about. Everything from there to the closing brace of that enclosing scope. So all the rest of the code where that variable is in scope, I want to examine. So I set that up, that's my bounds. And then I have the semantic model, and one of the things you can do with a semantic model is you can analyze control flow, or you can analyze data flow. In this case, we want to analyze data flow within those given bounds. And so now once we've done that, we can start writing these interesting queries again. So I can say, all right, for all the variables that are part of that declaration, get their declared symbol, right? So that's the other half. We got the initializer expression before. Now we want the actual thing you're declaring. So you're saying long x. You want the x. And so once you get the x, we then want to say, all right, well, within that region that we care about, is anybody writing to x? And if we look at what data flow analysis provides us, it gives us this really nice set of data here. It tells us, all right, well, here's the set of things that are read inside there, inside that scope. Here's a set of things that are written inside there. The set of variables we can assume are always assigned because every pathway to here guarantees that that variable is assigned. And so we have this kind of interesting data. This is the data the compiler uses to give you errors about things not being guaranteed to be written to or so on. And so we get to leverage this now and say, all right, well, let's make sure that the set of things that are written inside doesn't contain that thing we're trying to make const, because if it is, we can't make it const. So if any of them are written inside, then we return null. And so this is the last test. Once we pass this test, we've filtered out everything that couldn't be const. Now we know we're ready to tell the user to make it const. And so we go down here, and we return an array with one new code issue we're going to provide. We say it's a warning. We give it the span of the whole local declaration. That's what we want to squiggle. And we give it text to say, hey, you can make this constant. And so now, if we run again, we're going to launch our Roslyn instance of VS. I can now load this quick fix demo code project again. And now we've made this more useful. It's not highlighting everything that has an A. Instead, it's squiggling things that can be made constant. And so you see here int I equals 19. This is something that we're not writing to later. 19 is a constant literal. So I can go here, and I can make it const. And you see, we just wrote something that does some analysis of a node. But while I'm typing, the compiler is able to figure out what to squiggle. And now when I hit space here, it realizes that it should unsquiggle that because it called our logic again. We did our analysis again and realized this no longer has a code issue to report. So when we have to provide this kind of functionality today, we have to deal with all these IDE cases of you're modifying the code, what's actually changing here. And so we managed to handle all that for you. You just think about, I'm analyzing this node, does it have an issue or not? And so the other benefit of it being live is I'm typing const here. Once I hit space, you see now suddenly the next line is squiggled. I've made I and j constant, and so now, well, this expression here, this I plus j, has suddenly become a constant expression. So now I get a squiggle there, and I could go make that constant. And the cool thing is, right, I mean, this is within a single file, right? You could imagine these things are referencing across projects. Roslyn is thinking about it in that whole scope. But there's other kinds of solutions that are beyond just the MS Build kind of I'm inside Visual Studio solution. Think about that C# interactive window. In case you haven't seen it, Dustin and our team likes to say it's sort of the highest working set calculator you're ever going to encounter. But it does more than that. It does more than you could do in the immediate window today. It also lets you start defining things. So I could say here, void m, and start defining a method here, and then go up into that method. Let me just copy this code here. Go up into that method that I'm defining in the interactive window and continue editing it and paste this in. And you see that in the interactive window, I'm now getting squiggles in the context of this method body that I'm still defining. And if I go here, you see it says, can be made const, if I hover over it. If I go and make this constant, you see the same stuff is happening. I make this constant, and I'm immediately getting this kind of live feedback in this interactive environment. And so this is the power of having these abstractions. We name the types things like project and solution, but that can be virtual. It can be something like the interactive window or some other host or some command line tool or anything like that. And then we're able to surface this information up to you in whatever way makes sense for that environment. So, let's go back now to our code here. And, we have this code issue, we're surfacing it, but the one thing we really want to do is say, all right, well, you said it can make a const. It's pretty obvious what it means to make something const. Why can't it just do that for me? And that's that idea of code action, is actually providing the action to take the effect, to have the effect in the code that you wanted. So let's modify this and actually add that code action. So what I'm going to do is I'm going to go to my solution. I'm going to go collapse this. I'm going to add a new class. So I'm going to call this class code action. And I'm just going to start off here and just add some usings, right? So I'm pulling in some stuff I know I'm going to need. I'm going to sort of just get rid of this default code action and put in sort of the stub for implementing the iCode action type. This is another one of those Roslyn types. Lets me do stuff at the editor tier. And it has stuff that's probably pretty obvious. It has a string property that you get make constant. That's going to be our description for the action in that in the list when you pull up the smart tag. It could also have an icon. We're not going to have one for now. And really, like you remember the getIssues method I implemented, this is the same kind of thing. This is getEdit. So I'm going to implement this and return a given edit, given edit here. And that's going to be that transform that I want this action to do. I'm going to take in whatever tree I've got and then specify what the tree would look like afterwards and give it that edit. So the one thing I need is I actually need some data from the code issue. So I'm going to pull that in here. And if I take a look here where I'm actually finally creating that code issue object and returning it, one of the extra things a code issue constructor can take is a set of code actions. So I'm actually just going to say here, new code action. That's that type we're making. And I'm going to just kind of start passing things to a constructor that we don't have yet. Stuff I know we need. We need the local declaration in question. We need the document. And we also need something called the edit factory. You don't have to worry too much about what this is. It's basically just something that comes through from the constructor. And you need this to actually make those edits. So if you're going to make a code action, go ahead and pass it through to your code action. So I'm passing these three things in. This constructor doesn't exist yet, but I'm using the new generate from usage stuff. I'm going to make myself a constructor stub. I'm going to step in, and the compiler is nice enough to actually go make me some member variables to store this. Now I have access to this stuff that I care about. So there we go. I've now got all the data I need. I can start to actually declare my action. So at this point, I know there's an issue. I don't have to verify it anymore. I just have to declare what it means to go add that const token. So I'm going to go here and put this code in. And you remember a while ago we were talking about trivia and how tokens have this associated trivia. One of the things when you're dealing with having a rich edit that you want to do that doesn't interfere with the user's code is you have to just ensure that you're respecting the user's trivia as well. A lot of times it's automatic, but in some cases you have to think about it explicitly. And so here, you think about what we're doing. We're adding the word const to the beginning of some declaration. But there could be other stuff at the beginning of that declaration. There's white space of some amount that you want to keep. There could be a /* comment that's in there. And we don't want to lose that either. All of those would be leading trivia that's attached to that first token. And so we want to preserve that. We kind of want to snip that trivia off, insert our const token, and have that const token have the trivia reattached. So it's at the beginning of our new expression here. And so that's what we do. We go about getting the first token. We take the declaration, ask for its first token. We take that first token and ask for its leading trivia, the trivia that's before the token. And then we go ahead and make a trimmed declaration, right? We're taking our existing local and saying, go ahead and make a new copy of yourself that replaces that first token we found with a new version of the first token that has the leading trivia set to nothing. We just make an empty trivia list. So we take the trivia, we store it on the side, and then we replace the node with something that has no trivia. And so now that we've captured the trivia, we can make our const token. And we put the const token in and say, all right, make us a new token. It's going to be a token that is the const keyword. And the one thing it has is this leading trivia attached to the front. So we've kind of cut off the trivia, put our const token in, and put the trivia back on the front of our token. This is the kind of thing where you could imagine different helper APIs and things. This is the kind of stuff we're still exploring. So, all right, we now have our const token set up. There's a few more things to do. One thing, just for good measure, we're going to make this new modifier list, and const is going to be the one modifier that's in there. We could just add the const token by itself. Instead, we'll concatenate it to the list of any modifiers that are already there. Now, there's no other modifiers that are legal on a local inside a method. But again, being a good citizen of the IDE is being able to deal with error code. Maybe the user copied a module level thing into their method and they still have read-only there. When you make a const, we shouldn't be deleting read-only. If the user has it and it's invalid, well, they should still keep it so they get the error and they can think about what they want that to mean and what edit they want to make. So we take the modifiers that are there and we kind of glue const to the front, const with all of its trivia attached. All right, so now we have our new modifier list. So we know what that's supposed to look like. Now we can actually make our local. So we go here and we say, all right, well, we have the trimmed local declaration, the one that has the trivia removed. Go ahead and make an updated version of that that has our new modifier list, the one that instead of being empty or something weird now has const there. And reuse the rest of it. Reuse the declaration that we've got and reuse the semicolon token, right? Again, you want to reuse these tokens whenever you can. We could make our own semicolon token, but then if there was a comment right after the semicolon, we would lose it. So the easiest way is just flow the semicolon token through. It brings all its trivia with it. We've got that now. OK, we have a new local. And now I can go ahead and apply formatting. So what I'm saying here, this is another system that we've got. Let's just do simple stuff to say, I'm changing this node to one that is going to ask Roslyn to just auto-format it. Right? And so, we're changing some stuff around here. If you know you're making an edit that could affect white space, you can just ask Roslyn to ensure that snippet is formatted according to the rules for C# or VB, whatever you're in. And so we're just asking for that to happen here. And so finally, we've got everything set up. We've turned our declaration into a new local declaration, turned that one into a formatted declaration again. You're always making new nodes when you do these things because it's immutable. And now we're finally going to go do our replacement. So, the same kind of thing we did before. We get our syntax tree. We cast it to get a C# syntax tree. We go up to the root, and we tell the root we want to replace a node. And so the node we want to replace is the original local declaration, the one that we started with. And we want to replace it with this one we got to all the way at the end, the formatted declaration. The one that has const attached, has a modifier list that's updated, has the trivia fixed, and is tagged for formatting. We did all those things. That's the replacement we want to make. And this is going to go and it's going to do that tree surgery that we saw in the slides. And then finally, once we've got our new root, we can return the edit. And so now we can say, all right, well, here's the new shape of the world. And so let's say that this edit, what this edit represents is it's a tree transform. So if the user chooses to take this action, it's going to transform their tree and say, all right, for this particular solution, take the tree, the syntax tree that we're talking about here, and give it this new root. And that's the transformation that's going to occur when the user clicks on that particular action. So we can run this again. And there is a build error here. Let's see. I might still be running this. Yes. Run that again. Go in here to quick fix demo code. And we see that we have the thing here. OK, I don't think it built. Let me just rebuild it now. Go back in to quick fix demo code. Here we go. So now we've got our code issue, the one that we had before, but you notice now that there is a little smart tag icon that's attached to each one of those. And that's saying, hey, not only is it an issue, but we actually have an action you can take to go fix it. And so I put my cursor here, and I'm able to hit Control dot and bring this up, and we see the thing that we're working on here. And I'm just going to zoom in so you can see. And there's some really interesting stuff going on here. I'm saying int I equals 19. You can see on the left that that's squiggled in my actual code. But the preview that's showing is showing the result of the world once I do this edit. And so this is a result where that thing no longer has a squiggle, but it's actually able to run my test again in that potential future universe to say, if you were to do this and we were to analyze those nodes, then this is what would happen. And this is where you really start to get this next-gen benefit from having this thorough snapshot model that permeates everything. We can ask questions about something you may not choose to do, but we want to give you a preview of. So I can say, all right, in this case, go ahead, make that constant. And if I look here, this one is the awesome one. Well, so if I choose to make this one constant, remember, that makes the next one a squiggle when it wasn't a squiggle before. So I'm able to realize that that would be an impact of me making this change. And it's all just a natural consequence of the design that we have here with snapshots. And so I can go back here, I can make that constant as well, and then use that all the way down here. And so, who wants to bet whether this also works if I go back into the C# interactive window? I go here, I make myself a method. I go into the body of the method, I do this, I see the same thing here, I'm able to make this constant, and then, I look here and I'm able to get the same kind of logic going on here. And when I apply this here, it's happening just as it did in my source file. It's happening in my REPL. It would happen in any environment in which I'm operating. So this is that kind of rich power. And you think I'm getting all this benefit everywhere. I'm getting this code action. This is occurring in my file. It would work across solutions. And all I had to do was write this visitor pattern implementation, right? Say, what do I do at every given node that I see? I do the very sort of leaf node part that implements my actual logic that I care about. Again, which could be any kind of thing. It could be check-in tests. It could be all sorts of stuff. But I just implement the core logic, and I don't have to think about parsing code. I don't have to think about IDE race conditions. I just implement this one little thing I want to do, and the Roslyn infrastructure takes care of the rest. So that's pretty cool. So that's really it for this, for the demo. It was sort of a whirlwind tour of everything that you could do with Roslyn. If you really want to try this out for yourself, go try it out. We have the Roslyn CTP. It's up on the web. That's what I'm running on now on top of VS 2010, so you could do all the same stuff I was doing. There's a big set of samples that are provided there. You can figure out whether your tokens contain A, and you can do all sorts of other fun things. You can try out the APIs, most importantly of all, and give us that feedback, right? I mean, this is something that's evolving rapidly as we try it out, as we actually start to integrate it further. We want to make sure we have the API surface that's most useful for you guys, whatever it is that you think you could do that could really be awesome with the Roslyn API. Try it out, let us know, go to the forums and start posting on the forums, talking to other people, figure out what works for you and what doesn't, and let us know what we could make better. And if you have any specific feedback that you find out, feel free to email me, alextern at microsoft.com, and I'll pass it along, and we'll get this to be as awesome as it can be. Thanks.